Well, it's John Black, super chemist, here to show you how to get nitromethane. Um, there's a picture of a molecule of it. This is how I like to draw it. A couple names, a couple little facts about it. All right, here's some more properties. You can look at them yourself. This is the melting point. I like to call it the freezing point. Um, how soluble it is in water. You can get 10 grams of it into 100 milliliters of water. Its vapor pressure. It is acidic. I'll go into that, but it's got a pK of 17.2. Water's like what, 14 or something like that, and methanol and ethanol and that, they're like 16. So this is 17.2. It is acidic because of the pKa value. Um, it can go through the most famous experiment is the nitro-aldol reaction. Let me go back here for a sec. Now, do you see that molecule? Look how the N, okay, these are all electronegative, okay? But oxygen is more electronegative than the nitrogen. So it hogs the electrons, right? So the nitrogen, it asks for it's electronegative too. It wants those electrons back. But the oxygen's too big. It's like, screw you. But it's got this little puny carbon here that isn't that electronegative. So it can pull and it wants to get electrons. It's electronegative too. It doesn't want to be positive. So it snags some electron density from the carbon, and therefore when this gets deprotonated, what makes something easy to be deprotonated? Whatever's left has to be able to be stable, okay? Now, if I take this proton off, how am I going to stabilize that negative charge? Well, easy. You got this positive electronegative nitrogen here. It's positive and it wants to be negative, so it will easily snag up some of that charge and stabilize that. And that's how it can go through. Basically, it's the same as an aldol reaction, but instead of using two carbonyl compounds and making one into the enol would be your nucleophile. In a nitro aldol reaction, this is your nucleophile because you're going to deprotonate that in basic solution, and this will attack the carbonyl, and you'll make a beta nitro alcohol instead of a beta hydroxy carbonyl compound. Same exact experiment. And another thing that it is a great Michael donor in 1,4 Michael additions. It's great at that. All right, well, let's get into how you get this stuff now, okay? There's two ways you can buy stuff and extract. One is drag racing fuel. That's 90% nitromethane and 10% methanol. Or you can get RC fuel. Now, what is RC fuel? RC stands for radio controlled. It can be a car, a radio controlled helicopter, or whatever. As long as it uses fuel, like gas fuel, like, liquid fuel, not batteries, you'll have this. But it's only a 10 to 30% nitro, and the rest is methanol. So you got a lot of methanol in there. Keep in mind, they're going to add some oils in there. So I'm just making up numbers here. I mean, I'm just trying to give you the gist of it, okay? So there's going to be some, but these are going to mostly be high boiling, and they'll be left in the pot if you distill it. Now, purification, it freezes right here. Look down here. It freezes at minus 23 Celsius. Now, the freezing point of methanol is minus 97 Celsius. So if you took it down, you got some dry ice and made an ice bath that went down to, say, minus 80 degrees Celsius, right? This will freeze out. This will not. And then you can filter it, wash it with cold ether, and then you'd be left with your nitro and your ether, which you can easily separate from distillation. Keep in mind, if you distill nitromethane, it is explosive. All right, you do it at your own risk. Don't blame me for it. I'm just here giving some information. My information is if you kill yourself, it's your own fault. I would do this under a vacuum. I would actually do it under an aspirator vacuum or a slight vacuum, not a heavy vacuum. And I'll tell you that why later. But let's just do a little example here. Let's say you get a liter of nitromethane, and it's the kind that you got from the RC cars, the fuel. You're going to try to get to 30%, so that means 300 milliliters of nitromethane, 700 milliliters of methanol. Now, if you distill off 778 milliliters, that means the first 700 is going to be methanol, right? We know there's a 10% azeotrope with this, right? Or not 9%. So we divide it by 0.9, the 700, and that tells us that we would actually distill 778, all right? The 700 would be completely out, right? And then the other azeotrope part. Then you would be left with 778. Let's say 22 of it was oil and additives. So let's say 800. So you take 1,000 minus 800, you get 200 milliliters of nitromethane from every liter. The rest of the nitromethane is stuck in your methanol. I got nitromethane one time. It was like 15 years ago, and my buddy actually got it. He went to a drag race, and he said that I don't know if they still do it, or he got some, it was 90% almost. I mean, it was high. Let's say you went to the drag race and you went to the place where they're selling the nitromethane. I mean, they just sell them in gallons. Let's say you did that, then you'd have 900 milliliters, 100. You want to get rid of the 100, right? So you distill out the 100. How much azeotrope is that? It's 111 because I divided by 90%, right? So let's say, just to make even numbers, 40 of it or 39 of it is oil. So you'd get 850 milliliters of nitromethane from 1,000 milliliters of solution. All right, now I couldn't find a liquid vapor composition plot for nitromethane and methanol. So I had to find the vapor pressures of each individual whatever, and I plotted them. I figured out the math or whatever. So, this is a vapor liquid equilibrium chart or a liquid vapor composition chart, whatever. Basically, I have plotted on here. See this point right here? That is the boiling point of methanol. This up here is the boiling point of nitromethane, right? And I have this dotted line having a line from point to point. As you go like this, you know what I mean? It's going up. The more you go this way, the less methanol you have, and the more nitromethane, until you have all nitromethane, and it boils at the boiling point of nitromethane. If you have zero nitromethane, it boils at the boiling point of methanol. Now, if I have 100%, methanol right here, this is the boiling point. Now you would think, that it would be a straight line going up there, but it's not a straight line. This is the way it goes. Then your line here, this is 50%, 50-50. Go up to here. This is the boiling point. See how it curves? You can't really tell on my chart, but it actually curves down a little bit. And then it curves all the way up to here. See, this is why they call it a minimum boiling azeotrope, and they call it positive because that's a positive thing, I guess. Being lower, it's easier to distill it. But this is actually a lower point than this. But it's only like 2/10 of a degree or something like that, or 1/10 of a degree. I can't remember. It's really small. So trying to get this separated is like impossible, even up to here. But anyways, I just wanted to let you know that now this tells you a lot, this chart. Not the way I drew it, but if it was a correct, exactly correct. Because let's say you have, you can tell better over on this side. So let's say you have, it's 100. So you have 20% methanol, right? And you have 80% nitromethane. Look at how you come up here, straight up. Now this tells the composition of the liquid, right? But the gas is going to have a different composition. And the way you do that is you just do a line. You do a parallel line all the way over to here, and then you do a 90-degree turn down, and you can see what your vapor composition is. Now at this point, it's 35% nitromethane, and it's 65% methanol. Okay, and what was it down here? It was only like 20% methanol or whatever. You know what I mean? So you can see how it always moves. If you're on this side, it moves towards the azeotrope, and if it's on this side, it moves towards the azeotrope. It always goes towards the azeotrope. Anyways, I did mess up here because this should be moved over to here. Okay, so this point is where your azeotrope is, right? All right. Now what happens is when you have a positive boiling azeotrope like ethanol and water, or our example, nitromethane and methanol, uh, if you raise the pressure, this azeotrope moves, and it will move this way. So if you wanted to distill this, I don't recommend it, and you shouldn't do it. Especially, I'm afraid to do it, and I know a lot, but I would not do this. Uh, you can raise the pressure on this. You can move the azeotrope over, and maybe even to here, where it's pretty much all methanol. But when you put a vacuum on it, you move it this way, so you make it worse. Okay, that's why I say don't put a strong vacuum on it. You want a slight vacuum, so that way there's no leaks, and you know what I mean. You can run it through something at the end to get rid of it, so it doesn't get into the atmosphere and blow up. Um, so you will actually probably make your azeotrope go from a 9% to a 10%, but it's worth it. You know what I mean, for the safety. I always remember that's why, like ethanol, the pressures are so extreme that you would need to jump it up to where it's almost all ethanol, that it's not practical. So as you can see, if you have a 30% solution, 10, 20, 30, you go up here. If you distill it off, you're going to go closer to the azeotrope. Same over here, you're going to go closer to the azeotrope. So keep that in mind. Anytime you put a vacuum on an azeotrope, you move it, or at least this type of azeotrope, like the ethanol type of azeotrope and this type, you're going to move it this way. You're going to make it a worse azeotrope, right? If you put pressure on it, you're going to make it a better azeotrope. So vacuum distillation will never help you when there's an azeotrope involved, unless you can do high pressure. If you can do high pressure, then you can go back and forth and purify it that way. But that's beyond the realm of this video and this channel at this time right now. Maybe I will do a video where I distill the nitromethane out and actually, do it and show you how to do it or whatever. Now keep in mind, you can always, when you get done with you have your nitromethane, you should clean it with throw some calcium chloride in there, because it will it'll make a coordination complex with the methanol, and that way it'll turn into a solid, and you can distill it out. I mean, you can filter it out. The last suggestion I got is a guess. What you could do is add some water in there, soak up the alcohol before you distill anything, right? But as little water as you can, because you will soak up some of the nitromethane. If you get 10 milliliters in 100 milliliters of water, well, once the alcohol goes up inside there, it's going to be more soluble, or more, it's going to allow more nitromethane in there, because it's not water anymore, it's water and methanol. So you might soak up, you add 100 milliliters of water, you might soak up all the methanol, but you might soak up maybe 100, 200 milliliters of the nitromethane. I don't know. You'd have to experiment and see. It might be a good idea, though. Maybe add 100 milliliters and it'll only take out 50 milliliters. And we saw with a 1,000 milliliter thing that if you had a 30% nitro mixture and you distilled it, you'd only get 200 milliliters out. That means you lost 100 milliliters. So if this method works with just adding in the water, if you only lost 100 milliliters, it'd probably be worth it just to save on that distillation of trying to distill out the azeotrope. Anyways, give me time on my videos. I still haven't opened up my lab. But always remember, science is great.